Hi guys, welcome to Transverse Waves on a String, which is a lead-in PowerPoint for the core practical you'd be doing. I'll go into some more detail on that, whether it's appropriate to do so, but for now I just want to cover some of the key terms I know have been popping up on Isaac Physics that perhaps you're not ready for because we haven't covered the content, things like superposition, interference, etc. So this is the next slide and sequence, and you'll need to take some notes. There's some derived equations that are quite important, so make sure you've got your topic 5 revision sheet up and running, and make sure just the key parts, don't write everything down, just the key parts go on that revision sheet. Okay, so one of the things that you need to be wary of is how to treat a piece of string. So the question is what state is a piece of string? We're talking about what state of matter is in. Of course, it's a solid. Now, one of the things you need to be worried, reason we need to think about string as a solid is because people see a piece of string all floppy and able to move and start trying to treat it like a liquid. Well, they're not going to treat it like a gas, but treat it like a liquid. Whereas in fact, the energy transference is still perpendicular. You can't be a longitudinal wave. So we still need to talk about energy transfer as a transversal wave, so perpendicular to the direction of travel. Okay, so from this PowerPoint, we're going to cover literally the state of the equation for the speed of wave on a string. Okay, you need to know that equation, how to use it, where it comes from, and what's the purpose of. And we will use it to apply some problems. Now, where you'd often find this is in musical instruments. So I asked you guys to do something with find some xylophone videos. So if you've gone through this PowerPoint before, that's fine, but I just want to go through it with some of my notes as I draw and talk on it. Okay, so one of the terms that we've come across that in Isaac is coherent waves, and I know I did a little video that's sitting in the topic 5 folder on SharePoint on waves that are at the same frequency and on the same starting point, so the same wavelength start and finish points. So when they're coherent and their phases are aligned, we talk about superposition. So the two waves amplifying each other. Okay. Where this becomes important is when we have a standing wave. So if I start to, I'll try and actually start drawing some. So there's our wave. So if this wave starts here, travels along this way, I'll stop it there. Let me change colour. I've done wrong. Let's try green. Okay, so if I start this wave here, now obviously I can't draw it exactly. Ooh, otherwise it doesn't work. But these two waves here, you've got amplitude of the green, amplitude of the red. So what you'd actually have, it really doesn't want to play ball today. Let's go for orange. So the coherent superposition wave would actually look like double that. So I'll draw a little marker in there. So anything that this was material that this was traveling through would experience it as one big wave. And places you'd find this in the ocean, believe it or not. You'll see test questions where they'll show like typical wave heights, you know, big waves, little waves, you know, tiny little waves, medium-sized waves, and all of a sudden there'll be one giant wave on a graph, and this is a wave that's come along and both have been at the same phase, joined together, and you get this massive coherent superposition wave. Now, how does that work in standing waves? So we're now talking about reflection. I don't know what I've got on the next slide, so I will try and squeeze it down the bottom here. So if I've got let's do a guitar string. Okay, so guitar string is fixed at both ends. That's quite important. There has to be some tension on it. This doesn't work otherwise. And I will switch colours for this. Okay, so our wave, somebody strums the guitar string at a particular rhythm, at a particular frequency even, and that travels down the string, and it gets to that point. At that point, it's going to reflect the same way if I shout at the wall. And what actually happens is, if I don't draw over the screen, as it reflects, it's actually going to travel back, hopefully at the same frequency, on exactly the same path. Now, we've just talked about this up here. Stop pressing the buttons. This is now a coherent wave. It's culminating, and the culmination of all these is you get a lovely guitar, if you're playing it properly. You get a lovely frequency that is same as the two original waves, but the amplitude is going to be double. Now, that's all well and good if you're a great guitar player. However, if you're like me on the ukulele, there is a slight problem. You don't know what you're doing, and you strum the guitar, and we create a wave that hits there. Now, if the wave is, let me try and draw this more obvious. If the wave's on its way down, I'm going to put it there. I'll change colour. That's obvious. Okay, so I haven't got it tuned properly, and on the way back, I've now got. Hang on, I'm trying to figure out how to draw this. So it's going to be going down, so back up. So if I now have, oops, I'm slight. You get the idea. They're no longer, whilst they're at the same frequency, they're not aligned with each other. The phases aren't aligned, so we don't get this lovely double amplitude. In fact, we get this horrible grating noise here, and probably one down the bottom here. Okay, all because we don't have our perfectly synced waves. So when people tune guitars, this is what they're looking for. At the point where they're strumming the strings and suddenly the amplitude jumps up massively. So this is why people can tune a guitar by ear. You can just listen for the amplitude to suddenly increase. Okay, so wave speed in a string, this is where it all starts to come together into questions that you'll need to be able to solve your way through. And this is the formula for a wave speed in a string. Now, V is obviously for velocity, T is for tension, and U is for the mass of the string. I think these are all about to appear in a second. Where that's important is because there are 6 different strings on a guitar. They all have a different mass. Let me just press the key. Oh, there we go. Good. So there you go. Important notes underneath. Tension in newtons, that's per normal. Mass per unit length. There you go. Kilograms per meter. So there is a mass for each guitar string, and it will differ. They'll all be different. That's why you get different notes off each one. Okay, so there's a question for you to work your way through. So if you're obviously you're taking this on the SharePoint, you can, when you're ready, click through. Okay, so I'm going to assume that you've got some way of pausing when I stop talking, so you've got a chance to have a go at yourself. If not, just flick back to the start of the slide and pause me. But here you go, here's my working for you. So I've rearranged the equation, then yeah, I've rearranged it quite clumsily, but it works for what we're after. So 300 meters per second times 10 to the minus 4, 45 newtons. Okay, so if we wanted a quite quick wave through a fairly light string, needs to be quite a bit of tension on it. That's quite a thin piece of string, and 45 newtons is going to probably push it to its limits. There you go, there's a good topic 4 question for you on a different day. Oh, 3-minute timer running. Okay, so we need to know how we can derive for a what's called the fundamental frequency. So frequency, as denoted by our, oh, hang on, I've lost my pen. So frequency up here, okay, and the 0 means fundamental. So the F doesn't mean fundamental. Fundamental. Got to turn the other screen off. It makes my writing weird. Frequency, and the 0 means fundamental. Okay, so we've seen this. We just saw this equation. Okay, that's nice and straightforward. We know this from GCSE: velocity equals frequency times the wavelength. And we also know that the fundamental frequency will occur when the wavelength is 2 times the length. Okay, so we'll come back to that a little bit later. So wavelength equals 2 times the length. So when this will become more apparent when we actually look at where this is a starting frequency. This is the first standing wave. But obviously we want to be able to create different standing waves at different frequencies. But this is the first one. And this is the point where the first one occurs, 2 times the length. Okay, we start this with a completely blank screen. Oh, okay, so we're going to derive them together. Okay, so I can see we've replaced up here. This is just replacing V for frequency times wavelength, fine. Then we've times both sides by 1 over wavelength. That didn't come out well. 1 over wavelength. Okay, I'm assuming when I wrote this originally, I'm trying desperately to keep this together, which is usually, I'm not sure how you taught in maths, but normally with square roots in equations, you want to try and leave them alone unless you obviously have to rearrange for something that's inside. So then I've got, right, what have I got? For fundamental frequency, okay, so I've just swapped over the wavelength for 2 times the length. Okay, so now I have this lovely big equation for the fundamental frequency, and this is the kitty. So we need, obviously from the previous page, velocity equals the tension over the mass per unit of the string, square root of which. So we need that equation, and we need the fundamental frequency equation. And then it's just in red, just because it is. Okay, so question for you to try. I'll stop talking. I'm not sure if there's working out after this, but I'll stop talking. You can pause it, or obviously flick back to the start of the slide, and I'm not sure how you guys can play these out, and then have a try at it, see what you come out with. Okay, so hopefully you've paused it, and I'll flick onto the working out. So I've taken the fundamental frequency equation, substituted in all the values, so 2 times the length. So, of course, watch out for conversions between centimeters and meters. Catches people out. This was from earlier in the PowerPoint. We had our 45 newtons from earlier. That's where the tension came from. And we've already been told what string is. And I have absolutely no idea what the answer is. I don't think it's going to appear. But if it doesn't make sense, let me know. Actually, I'll tell you what, I will pause it myself. Okay, so I just punched that into the calculator, and I got 236 hertz. So if you get anything different, please feel free to email me. I'll obviously pay lots of attention to it and ignore it promptly. Okay, so the core practical, I would have literally given you some string, a vibration generator, and you're going to create a standing wave. What I would like you guys to do, obviously because you can't do the actual practical, is take that equation, go back a step. What happens if you vary the tension? Chuck some numbers in. So if you increase the tension, what happens to the speed of the wave? What happens to the frequency if you vary the tension? What happens if you vary the frequency, etc.? There are lots of things that you can change around, and those are the kind of questions you get. a student conducts this experiment and increases the tension. Explain what the result would be. And you would obviously need to use the maths to demonstrate that you understand the mathematics behind it, but also what is going on, what's changing in the equation and what effect that has. So that's something that you probably want to draw on your revision document. A little arrow going, increase the tension, what happens? And if you increase the tension, what would happen to the speed, frequency, etc. Okay, so there's lots of moving parts there, and you could just draw little arrows around the equations stating what would happen if. Into the PowerPoint, I'm going to try and get one of these out of date here. Take notes, any issues per normal. Now, in terms of the material that I've set you on Isaac, until we cover all of the parts of Isaac's asking, some of the questions are very complicated, until you've got all the bits and pieces you need, I think you'll find it quite tough. So what I'd like you to do, as we go over the key parts that you perhaps weren't sure on, go back to Isaac and finish off that last assignment set. And when it's totally complete, and I'll be looking across the board, see where everyone's up to, then I'll set a new one. I don't want to overload you with tasks just to do just because. At this point in time, I just want to make sure you're making good topic 4, good topic 5 notes, so when we come back, we can just hammer out the core practicals, and you haven't lost any time. Any questions? Feel free to send me an email, and as per usual, I can try and give you a nudge in the right direction. Take care.